So that's under receptors again, sequences, and then sequence alignments. And this is actually a new selection page. We've adjusted this at the end of 2020. And as you can see, it has some elements of the other selection page that I've just shown you, but it has been adjusted in such a way that it's a bit more advanced to use. Well, not more difficult, hopefully, but you can do more advanced things with it in an easier way. So you still have the filtering options at the top for the species and the source, and you have the browsing options here. And then using these browsing options, it's interactive actually with this table underneath. So with this table underneath, you can select which receptors you want to align and what you want to compare. So let's take, for example, the aminergic receptors, and we take the histamine receptors. So then they're automatically highlighted here. But you can also directly use this table format. And let's, for example, take the opioid receptors, because some opioid ligands actually have some interactions with the histamine receptors and vice versa. So it might be interesting to see what's going on there. So here now I have selected the opioid ligands as well. Opioid receptors, I'm messing up ligands and receptors and stuff, but anyway, and now at the top you can see that there are 8 targets selected, and we have this small button here for if you want to check what is selected, you can hide everything that's not selected, and then you can get this nice overview. Within this overview, you can, for example, also get information about the number of ligands that are known for a receptor, the number of structures that are available, specific PDB codes if they are known, and also some information about G protein coupling. So that might, for example, influence the choice of a receptor. In this case, I'm just going to look at humans, so I'm going to keep the species and human. And then the next step of a sequence alignment is to indicate what you want to align. So do you want to align the whole sequence, or do you want to focus on specific areas? Because, for example, it could also be that you're very interested in just one transmembrane helix or a specific loop. But for now, I'm just going to go with all the elements for which we have structurally conserved generic position. So that's where we have this numbering scheme. And then here on the right, you can see a sort of a summary again of your selection. So we have the selected targets again, so the ones that you've selected, and you can also modify it here if you're not happy with the selection. And also the selected segments are highlighted. But for now, I'm happy, so I'm going to continue to the alignment. And that, depending on how big the alignment is, it can take a while, but we've been optimizing this, so hopefully not too long. And that brings you to this page. So here we have the nice alignment for each individual segment. Each individual segment is highlighted. Here we have the receptors that are highlighted, and you can click on these again to jump to the specific receptor pages. So you can just go through this, and the coloring is now based on the properties of the amino acids. So the coloring shows also maybe some level of conservation. In addition to that, we have at the bottom here, we have also at the top, we have the sequence numbering. So the by Sayers-Weinstein numbering in this case, and the structure-based numbering, and it's also repeated here. And that's for if we have very long sequence alignments of a lot of receptors, then you don't have to scroll all the way back and forth. Then you can always find it. And below here, we have consensus options. So that actually analyzes what information is conserved within this alignment. So if we look, for example, here at transmembrane helix 3, we see a lot of aspartic acids at position 332. And that's actually the main ionic anchor, the main interaction partner of both opioid ligands as well as histamine receptors. So that also already gives us a clue. And that's what we also see here in the sequence consensus. So in green, we see that this aspartate is very green. So that means that it's highly conserved and it's also 100% conserved. The GPCRdb actually goes one step further. So it does not only analyze the conservation of specific amino acids, but it also looks at what properties can be conserved. So for example, if you have aromatic residues at a specific position, or you have polar residues at a specific position. And that's what's being highlighted here in this very long list of residue properties and length. So based on the length and the properties of the residues, we actually analyze what the level of conservation is. So even though you might not find a conservation directly in the residues themselves, maybe you can find conservation within these specific properties. And that's completely being analyzed here. And also at the beginning here, it's color-coded. So that's, oh yeah, one thing that I forgot to say is that also the length of the amino acids is being analyzed. So also the type, the length of the residues, of the side chain is being analyzed, and what level of conservation is linked to that in combination with the features. But we'll talk about that a bit more in the next Dr. GPCR Virtual Cafe, because then we're going to go more deeper into also this sequence signature tool where we exploit this data even further. And the same as in all the other tools, actually, you can hover over all the residues again to get more information. For example, what is the specific numbering of this residue, and what is also the generic numbering of the residue. At the top left, we have a download button, as per usual. The Excel download is the closest one actually to what you're seeing here. So you get a formatted Excel file, including all the coloring and all the numbers and everything. And then we also have the FASTA download, so you can pop it automatically in your sequence alignment tools that you have. And the spreadsheet is a bit more raw. It's just the raw data actually of the sequence alignment. So I'm going to now do the sequence alignment once again. But in this case, I just want to for example, check out the whole class A. And then I'm going to show you why this segment selection is actually very nice to have. Because we just saw that the position 332 was highly conserved for the opioids and the histamine receptors. But what if you want to know more about that specific position for the whole class? So that is something that you can do. And if you at the next step in the segment selection, go to TM3 and then click on the small arrow, and then you can select each individual residue that you want to explore. So if I go to the end of this long list, I see we now only have position 332 as a selected segment. And then if we go to the show alignment, we see that actually quite a few receptors have an aspartic acid at this position, but also there are a lot of other variations at this site. So that might give you also a clue about off-target effects and also how special it is that a residue occurs at a specific site. Of course, it's interesting to see what the conservation again is. And apparently for the whole class A, we have that, we now see that the aspartic acid is the most conserved actually for all the amino acids, and the conservation is 20%.